This is Radio TV Phono Nut, and here is part 2 of the battery eliminator project. Just to give you a brief recap, well, maybe not so brief, I don't ever do anything briefly, but in a recent video we attempted to repair one of these circa 1940 Silvertone power supplies. It's designed to provide 1.5 volts and 90 volts for battery operated farm radios. They were designed to allow the radio to operate on standard 120 volt AC. Well, we got everything recapped and all that, and new rectifiers, but our A supply filament voltage was not quite what it should be, and I come to the conclusion that the original transformer might have been defective, which may or may not be the case. I'll get to that in a minute. But as I stated in that video, the main disadvantage of these types of power supplies is there's no kind of voltage regulation. What you get on the output largely depends on how much is going in from the AC line and the load placed on the power supply from the radio. And like we talked about, if something goes haywire with the radio, then there could be too little or too much filament voltage on your tubes, which could damage the tubes. Now, Shango066 brought up something in the comments that I hadn't thought of. He mentioned that possibly the copper sulfide rectifier had less voltage drop, even though maybe slightly less than a silicon rectifier, which typically has 0.7 volts drop across it. And he suggested that maybe the silicon rectifiers had just a little bit too much voltage drop, and that's what was dropping our filament voltage down just a very small amount, just enough to keep the tubes from working. Well, I'll remember that in the future. He recommended that I use Schottky diodes because they have a lower voltage drop, and in the future I'll remember that, but I'd already torn this apart, and I'm not going to try to reconstruct it, so we're going to just do this like I had planned. At the end of the last video, we're going to build a new power supply in this case, and this one will be regulated, and we'll put out a constant voltage regardless of the AC line input or load placed on the power supply. Of course, that's all in reason, of course. Here's the transformer we're going to use. This is a little dual output transformer available from Antique Electronics Supply. The black wires should be our primary 120 volt AC input. The red wire should be our high voltage. I think this puts out, I don't remember, 120 or 150 volts AC. We can deal with it, whatever it is. The green wire should be our low voltage, 6.3 volts. I think the low voltage winding is rated for 300 milliamps and the high voltage is rated for 15 milliamps, so it's about the equivalent of what was in here originally. Now I've got to decide where I'm going to place everything, and in this bag is bunch of solid state components and other things that we need that I ordered from Mouser Electronics. So let me get to thinking here and decide where I'm going to place this stuff. Okay, we have the transformer soldered to the chassis, and the reason I did that is, like I think I said in the last video, I want to make this look from the outside just like it did originally. I don't want any bolts or anything sticking through. And we have our primary connections made. We have our AC voltmeter connected to the secondary high voltage winding. Now let's just plug everything in and see if everything works right. And as you can see, we have plenty enough room here to add our secondary rectification and regulation circuitry. Alright, here we go. 122 volts, that's exactly what I want to see. Now let's move to the low voltage winding. 12 volts. Okay, I said 6 volts, but I was wrong about that earlier. It is 12, but we can work with that. We can regulate that down to 1.5 volts DC just fine. Alright, now I need to connect our bridge rectifiers across each winding, one for the low voltage and one for the high voltage. Of course, I could have made these out of 1N4007 diodes, but it would look a lot neater to just use a couple of bridge rectifier modules, such as these things. They're rated for 1 amp at 600 volts PIV, so that's ample enough for what we're doing here. And if you notice, there are symbols by each terminal, the 2 in the center with the sine wave symbols. That's your AC input, the plus is your DC output, and your negative goes to circuit ground. Okay, we have our bridge rectifiers in place. This one's for the high voltage, this is low voltage, plus minus, and no, these grounds are not tied together. They'll be independent of each other. Okay, here's our low voltage regulator circuit, built on a terminal strip, and this should give us 1.5 volts output. These diodes wired on here are just a safety precaution in case the regulator should fail. It won't allow the low voltage to jump up to something that could burn the tube filaments out. The heat sink is something I just robbed off of an old circuit board. I had to put it on in that direction because if I put it on the other way, it would stick up too tall and the lid wouldn't fit back on the power supply, so this should still work out okay. Alright, we have the low voltage section mounted. Now let's flip the switch and see if we have the proper output. 1.52, beautiful. Alright, I have my sockets wired, the meter probes in the appropriate connecting holes, and we have 1.528. That's what I want. Now let's work on the high voltage side. Alright, for the exception of the Zener diode string across the high voltage output, there's our high voltage section done. And I screwed up. You see where I put an extra terminal strip here to support this bridge rectifier? I intended to do the same thing here, but just forgot all about it, but it don't matter. It's stable enough. I have solid wire connected from here to this terminal strip, so it's not going anywhere. I could have probably done the same thing here and not even needed this terminal strip, but oh well, this is more of a prototype anyway. Like I said, I have this completed except for the Zener string across the high voltage output. I'm going to connect my resistor box across the output so far to give it a load, because I want the caps to drain whenever I unplug it. And we're going to check our output voltage and see if we're working up to this point. Alright, here we go. It's either going to work or blow up. I didn't see nothing on my meter. Okay, so what's the matter here? Okay, no problem at all, except my meter probe just wasn't making good contact in the socket. 160 whopping volts here. So yeah, that needs to be regulated down. And this is why I had the resistor box connected to it. I want that charge to bleed down, because with no load, that filter cap would hold a whopper of a charge on it. Alright, I have my 4 22 volt 1 watt Zener diodes ready. We'll just wire them in series, and you can see this supply has provisions for taps should your radio be the type that requires more than 1 B+ voltage. However, since this power supply is designed for 1.5 volt and 90 volt, we won't be utilizing the taps. And I think if I were doing this, I would add another zener or two to this, because some radios require 135 volt D+. So I would reconfigure this if I was doing it for anything other than what we're doing it for. Okay, here's our zener string ready to go, and I'm sure some of you are saying to yourself, or asking yourself, why didn't he just order a zener diode of the right voltage? They do make such a thing. Well, yeah, they do, but I figure with these 4 in series, I've got a little margin of safety. If I only used one and it shorted, that could cause some problems. But with 4 of them, hopefully all 4 of them won't short at the same time unless something sure enough major catastrophic happens. Alright, the zeners are in place and we have about 91, 92 volts. This time I don't have a load on it, and you see how long it's taking to discharge. Okay, here we are about done. I'm about ready to go fetch a radio and see how it works. I did add, it's not on the schematic that I printed out, but was on the original schematic, the AC line bypass capacitor from one side of the line to B-, a .015 safety cap, just to kind of suppress the noise on the line. Now let's go fetch a radio and see what it does. Alright, there we go, connected, and as you can hear, it's playing. Now let's connect our voltmeter. Turn the sound down, you know it works. Let's connect our DC voltmeter and check our voltages under load. Alright, running 89, well, we'll just round it up to 90 volts under load on the B+. And 1.52 on the filament. Great. Now let's let this thing play a while and make sure nothing overheats or blows up. And then this thing will be ready to go. In the 116th Congress, 9,621 pieces of legislation were introduced. Only 203 had the words climate change in them, even though that 70% of adults, 90% of kids believe that climate change is real. You know, these ones that are pitching a fit about the environment are the very ones that are the type when a new flat screen TV comes out that has a little bit bigger screen or a few features that their old one didn't have, they'll dump the perfectly good one. Or when the iPhone 11 comes out to replace the perfectly working iPhone 10, they'll dump the iPhone 10 to get an iPhone 11, and you know the cycle just continues. And we have all this modern throwaway garbage that either it goes in the dump because either people think they have to have the latest and the greatest all the time, or because the stuff just doesn't hold up. Well, me, I'm listening to this radio here that's almost 70 years old. Mortgage interest rates have dropped, and I'm perfectly fine with it. Right now is the time to I like to say that I'm the ultimate recycler. I get this old stuff and fix it up and use it or pass it along to somebody who will, instead of it going to the trash heap. If rates go up, your low. Okay, as far as temperature goes, the big power resistor in the high voltage side is running cool. The zener diodes are running cool. The biggest heat producer is this LM317 regulator on the heat sink, but I don't think that'll get hot enough to really cause any major problems in the future. If I redo one of these, I may have to it might be better to forego the cosmetics and figure out a way to mount a heat sink on the back of the case, and of course insulate the heat sink from the case and just mount the regulator on the back so it'll have plenty enough room to breathe. And then I might want to add a fuse to this. They don't specify the value on the schematic, but I can just take a current measurement with the power supply operating a radio and just come up with a fuse based on that. The transformer gets a little warm, but nothing to worry about. Alright, there you go. It's all put back together and ready for service.